One of the most powerful techniques that we can use rotational equilibrium for is to actually see the forces internal to a structure. So we're going to do that with this example using a truss structure. The truss structure, this is actually taken right from, those of you that have or know the book, Form and Forces by Edward Allen. This is page 131. It's that example. So because we have two loads of 100 kips, this is a very high load. This might be from a highway or a railroad bridge. They're symmetric, therefore we have a reaction on the right-hand side of 100 kips and a reaction on the left-hand side of 100 kips. Now the thing about this technique is that what we're doing is essentially cutting open the structure and looking inside. And those of you who have some other experience with statics may understand this as what is referred to as the method of sections. For analyzing a truss, but we're just going to look at it in a more global sense and call it rotational equilibrium, because that's what's really happening here. So this dotted line that I have drawn here, this is going to be our cut line. And what this means is that this is the point where we're going to saw through the members. We could physically do this. But in order for this to stay stable, we have to replace the internal forces with external loads. So let's redraw this portion of the structure. So we have something that looks a little bit like this. It has a load down of 100 kips and a reaction on the right-hand side of 100 kips. Now this is balanced in a linear sense, but it's not rotationally balanced. So for that to happen, we have to replace the external or the internal forces with what are, in a sense, external loads. Now this begins to reduce to a much simpler problem. Now there's also a force on the diagonal here that we don't know either. So these three forces are necessary to balance these two loads to keep this whole thing from spinning, because as we see here, we have a couple between these two. So the couple simply wants to rotate this whole object. So we have to balance that with these other forces. Now if we replace this with a simplified version, what I want to do is find a location that will eliminate all but one unknown, because with one equation for moment equilibrium we can solve for one unknown. And by picking this bottom joint down here, we can see the line of action of this force, the line of action of this force, and the line of action of the applied load go away. So in effect what we are reduced to is only two forces. This is member J that's labeled on the diagram. So this is, we'll call this P of J. And then it has a line of action like this. So its moment arm is the distance between that line of action here and a line parallel to that line of action going through the reference point. So the reference point will be on joint 2 in this case, and this is 16 feet away. Then we have a vertical reaction on the right hand side, and the truss is defined as 24-foot spaces between the panel points. This force has a line of action like so, a parallel line to that line of action passing through point 2 is 24 feet away. So we can see this is really quite a simple equation. If I sum moments about point 2, we'll call clockwise positive, I have my force P of J, which is what I'm looking for, at a distance of 16 feet. And relative to this point, it would rotate clockwise, so this is positive. My reaction, 100 kips, is 24 feet away. Now I wrote plus there, but this is rotating counterclockwise, so this actually should be minus. And if you mess up, if you guess wrong, you will get a negative answer, but the correct magnitude, so it just means that your sign was reversed. So force Pj is then 2,400 kip feet divided by 16 feet. $100 kips, 24 feet, divide that by 16. And that gives us a force of 150 kips in member J. Now, if we want to solve for the force in member M down here, we have to choose another moment center. And the place for that would actually be beyond our cut. If we go to joint 1, which is back up over here, even though that's off our cut, we can still do that because we can sum moments anywhere. If the rotational equilibrium is true at one point, it's true on any point. But by going back to this point up here, the force that's in the diagonal member passes through joint 1 as well as Pj, so it goes out of the equation. That leaves us with only these three: the unknown force in M, the 100 kip force down, the 100 kip force up. And we know distances for all of those items. So we create another rotational equilibrium calculation. Let's just draw this on top. So I'm going to do another coordinate system. This time, the top center over here, joint 1, is our moment center. And I've got a force over here. Of 100 kips. Force here of 100 kips. Then I have my unknown force, which we'll call M. And this is what we don't know. But what we do know are the distances. So I've taken the line of action, a line parallel to that line of action going through our reference point, which is point 1. And it's 24 feet between each one of these. Since we're talking about a symmetric condition, slide this back down. Talking about a symmetric condition here, so this joint is 12 feet away from here. That means this is 24 plus 12, or 36 feet, to that joint. Then this is the 12 feet here. Our vertical distance is the same as the previous one. It's only 16 feet. And now we have everything that we need to solve our rotational equilibrium equation. So I'm going to sum the moments about joint 1. Called clockwise positive. So we have three elements that rotate around there. 100 kips with a moment arm of 12 feet, right hand reaction, moment arm of 36 feet, the unknown force in P of M at a distance of 16 feet. So let's take the 100 kips at 12 feet, that wants to rotate clockwise, so it's positive. Well, our right is 100 kips, so we'll just put that in here. Moment arm here is 36 feet. This is going to be a negative sign because the rotational action goes counterclockwise, and I've called clockwise positive. And then the force in member M is 16 feet away. So here's the line of action of M. Parallel line going through our reference point is 16 feet. And that would, I'm going to guess that that is a tension action because on the bottom surface of the structure the fibers are pulling away under a gravity load, therefore it's pulling away from the reference point. So that would be a clockwise rotation relative to here if that goes from the right to the left. And that all balances to 0. So that means that the force in member M is going to be 3,600 kip feet. That's this. Minus 1,200 kip feet divided by 16 feet. So again, I have 2,400 kip feet divided by 16 feet. Feet are going to cancel. And again, this member also has 150 kips. Okay, so if we go back to our original truss then and put these numbers in, we have the force here. This member is labeled J, so P of J is 150 kips. And then the force P of M is also 150 kips. So in this instance, if we sum forces vertically, we have negative 100 kips down plus 100 kips up, the reaction. So this is already equal to 0, so it's vertically balanced, but it also, if we sum forces horizontally equals 0, we have a 150 kip force in the member J, and then another 150 kips in the member M. 150 minus 150 is 0. So in this case, this truss is actually balanced with 0 force in this diagonal member. We'll talk about 0 force members in another video, but that solves this truss for these two horizontal members.